On October 29, 2025, at exactly 11:15 a.m. Universal Time, an object from another star system, a messenger from an unknown cosmic shore, performed an impossible feat. It dove closer to our Sun than the planet Mercury ever dares to travel, accelerating to speeds of over 68 kilometers per second, a velocity so extreme it surpasses any comet or asteroid humanity has ever tracked. But here is the part that should send a shiver down your spine, the part that makes absolutely no logical sense. Not a single telescope on or off this planet captured the moment. Not one of our billion-dollar observatories recorded its perihelion, that critical instant of its closest solar approach. Not one astronomer, professional or amateur, witnessed the moment this interstellar visitor endured maximum velocity, maximum heating, and maximum stress on its very core. Now, think about this. For the first time in human history, we weren't caught by surprise. This wasn't a fleeting glimpse of something disappearing over the horizon. We had 5 full months of advanced warning, 150 days to prepare every single instrument we possess, from the mighty James Webb Space Telescope to the legions of ground-based observatories spanning every continent. We had time to plan, to coordinate, to aim our collective technological eyes at this one specific point in space, at this one specific time. And yet at the one moment that mattered most, we were completely, impossibly blind. It was as if a cosmic curtain was deliberately drawn across the stage, and new, deeply unsettling evidence suggests there may be a very specific, almost intelligent reason why we couldn't look. If you've been following the enigmatic story of 3I Atlas since its discovery, you already know that the official narrative, the simple story of a fast comet, just doesn't add up. But if this is the first time you're hearing about what truly happened on October 29th, then hit that like button right now, subscribe so you don't miss the next chapter of this investigation, and please, drop a comment telling me where in the world you're watching from tonight. Because what we're about to uncover goes far beyond a simple missed photo opportunity. In the next several minutes, we are going to dissect precisely why October 29th should have been the most observed, most documented, most celebrated day in modern astronomy, and why, instead, the very star that gives us life, the Sun itself, became an impenetrable barrier, a perfect shield between us, and a phenomenal, potentially world-altering truth. So, settle in. Let us find out what really happened during those crucial moments when we weren't allowed to look. Let's begin by painting a clearer picture of the sheer magnitude of what was at stake. The discipline of astronomy, at its core, is an act of patient observation. We have spent generations building a global network of sentinels, silent guardians whose only purpose is to watch the sky. We've been tracking asteroids, comets, and near-Earth objects for decades, with an ever-increasing level of sophistication. Our technology today is something that would have seemed like pure sorcery to astronomers just a century ago. From the mountaintops of Chile to the plains of New Mexico, massive arrays of telescopes scan the darkness, capable of spotting rocks the size of a city bus millions upon millions of miles away. We can predict their trajectories not just for next week, but for the next century, with a mathematical precision that is nothing short of breathtaking. We have eyes in the sky, like the Hubble and the James Webb Space Telescope, positioned far beyond the distorting veil of Earth's atmosphere, giving us a crystal-clear view into the cosmic abyss. We have satellites, a whole fleet of them, dedicated to monitoring our Sun from every conceivable angle, tracking its every flare and eruption. Our ground-based radar systems, like the now-lost Arecibo Observatory once did, are so powerful they can bounce signals off objects hundreds of millions of kilometers distant and create detailed surface maps from the returning echoes. We are, by any measure, a civilization that has mastered the art of looking. And yet, on October 29, 2025, when 3I Atlas, an object we had been meticulously watching since July of that year, made its climactic closest approach to the Sun, we saw absolutely nothing. Let me be perfectly clear. This wasn't because of a technical glitch. It wasn't because of budget cuts or a sudden solar flare that fried our instruments. It wasn't because we weren't looking. It was because we couldn't look. The failure was absolute, and it was a failure of geometry, of a perfect, almost preordained alignment of celestial bodies. The object was positioned in a cosmic blind spot, a sliver of space behind our Sun, where our vision simply could not penetrate. So, what exactly did we miss? What was happening in that unobserved moment? Astronomers had a detailed checklist, a holy grail of data points they expected to collect during perihelion. They were prepared to measure the exact split-second moment of its closest solar approach, which would have allowed them to calculate the most precise velocity changes as the object accelerated through the Sun's immense gravitational well. Any deviation from those predictions, no matter how small, could have pointed to outgassing or even more exotic, non-gravitational forces at play. They desperately wanted real-time spectroscopic data. As the object skimmed the Sun, they expected to see its nucleus subjected to extreme solar heating temperatures hot enough to vaporize ancient ice from its surface and release gases that had been trapped deep within its core for potentially billions of years. The light from these released gases, when passed through a spectrometer, would act like a chemical barcode, telling us exactly what this visitor was made of. Was it like the comets from our own solar system? Or was it composed of something different? Something that could only form in the crucible of another star's planetary system? Furthermore, they planned to track its rotational changes with unparalleled precision. Was it stable, or was it tumbling chaotically? The wobble and spin of an object like this can reveal incredible details about its internal structure, its shape, and how its mass is distributed. Is it a solid, coherent body, or a loosely bound pile of rubble? Surviving a 68-kilometer pass by the Sun requires immense structural integrity. Observing how it handled that stress would have answered that question definitively. And perhaps most importantly, they hoped to capture the very moment of maximum outgassing. This is that brief, spectacular window when the coma, the fuzzy atmosphere of gas and dust around the nucleus, would expand most dramatically. In that fleeting instant, chemical signatures that are normally too faint to detect at greater distances might become visible, revealing the object's deepest secrets. Every major telescope with the capability was, in theory, ready to go. Every astronomer who understood the historic significance of a third-ever interstellar visitor, and the fastest one at that, had marked their calendar. October 29th was supposed to be the day we finally got clear, unambiguous data. The day we could definitively say what 3I Atlas actually is. Instead, they got silence. They got a blank screen. They got nothing. And the reason for this colossal failure is as simple as it is profoundly frustrating. An inconveniently perfect alignment known as solar conjunction. It is a moment that raises a deeply uncomfortable question. Was this perfect cosmic hiding spot just a random roll of the celestial dice? Or was it something else? To truly grasp the frustration, the sheer helplessness felt by the astronomical community, you need to understand what solar conjunction really means. Not in technical jargon, but in practical, visceral terms. Imagine you're a detective trying to observe a suspect across a vast open field. You have the best binoculars, the best cameras, you're ready. But just as the suspect is about to make the critical move, someone drives a giant, blindingly bright searchlight on a truck and parks it directly between you and them. The light is so intense you can't see anything around it. Your equipment is useless. You risk permanent damage to your eyes, or in this case, your telescope's optics, if you even try to point it in that direction. That searchlight was our Sun. Starting around the 1st of October 2025, 3I Atlas began its inexorable journey into this observational dead zone. From our vantage point here on Earth, it appeared to move closer and closer to the Sun in our sky. This is measured by something called angular separation. By October 21st, a full 8 days before it even reached perihelion, the object had slipped into a zone with less than 30 degrees of angular separation from the solar disk itself. For any ground-based telescope, this is an impossible situation. The ambient light from the sun scatters through our atmosphere, turning the daytime sky blue and making it impossible to see faint objects. Pointing a sensitive, multi-million-dollar telescope anywhere near the sun during the day is a recipe for catastrophic failure. You risk literally melting the delicate sensors and optics that are designed to capture the faintest whispers of light from distant galaxies. The heat and light are simply too extreme. But what about our space telescopes? Surely they're above the atmosphere and don't have this problem, right? Not exactly. Even specialized solar observatories like the Solar and Heliospheric Observatory, SOHO, are designed with instruments called coronagraphs. A coronagraph is essentially a small, precisely positioned disk inside the telescope that blocks the overwhelming brightness of the sun's main body, allowing the instrument to see the much fainter outer atmosphere, the corona. It is like using your thumb to block out the sun so you can see something flying nearby. But even these specialized tools have their limits. They struggle to observe objects that are extremely close to the solar limb. And 3I Atlas wasn't just near the sun in our sky. On the day of its closest approach, its trajectory carried it almost directly behind the sun from our perspective. It was a perfect bullseye alignment. This impenetrable celestial blind spot wasn't a brief flicker. It lasted from the first weeks of October all the way through the first weeks of November. For more than a month, the most fascinating, most anomalous, and fastest interstellar object we had ever tracked, with advanced warning, became completely and utterly invisible to every significant Earth-based and Earth-orbiting observatory. Now, think about the timing of that. The object reaches its most interesting point, perihelion, on October 29th. The astronomical alignment that renders observation impossible, solar conjunction, reaches its peak on October 21st. 8 days of separation. 8 agonizing days during which the comet was completely hidden behind the most luminous, most electromagnetically loud object in our entire solar system. It was unreachable by our most powerful tools of optical and infrared astronomy. 8 days when absolutely anything could have happened, and we would have no way of knowing. Now, I need to be fair and clear about what we did manage to observe during this period, because it wasn't a complete and total blackout of all information. This is where the story gets even more tantalizing. NASA's GOES-19, which is primarily a weather satellite positioned in geostationary orbit to monitor solar activity and Earth's climate, managed to capture fleeting images of the object between October 18th and October 24th. The comet appeared as a magnitude 12 object, bright enough to register on sensors that were never, ever designed for deep space astronomical observation. This is like a security camera designed to watch a parking lot accidentally capturing a clear image of a hummingbird hovering for a split second. The Solar and Heliospheric Observatory, or SOHO, which sits at a stable gravitational point between the Earth and the Sun, called the L1 Lagrange point, also recorded heliospheric data during the passage, confirming its trajectory through its coronagraph. These satellites gave us something. They were our proof of life. They confirmed the object was still on its predicted path. They verified it hadn't disintegrated prematurely, and they provided very rough estimates of its brightness. But they didn't, and couldn't, give us what we truly needed. They couldn't perform the detailed spectroscopy to read its chemical barcode. They couldn't measure its precise rotational dynamics to understand its structure. They couldn't capture the subtle spectral signatures that would differentiate a normal, boring ice and rock comet from something far more unusual. They saw it pass, but they didn't see what it was doing during that passage. And here is where the story shifts from frustrating to deeply strange. This observation gap wasn't a surprise. It wasn't a sudden, unexpected event. From the moment astronomers calculated 3I Atlas's trajectory back in July, they knew. They knew perihelion would occur during this perfect solar conjunction. They had 5 months to plan, to devise alternative strategies, to get creative. And yet, when October 29th arrived, we were left watching from behind an impenetrable wall of solar radiation. That's not just bad luck. That's not a simple oversight. That is the cold, hard, inevitable consequence of orbital mechanics. But it leaves us with a gaping question that no one in the mainstream seems to be answering. What happened during those 8 critical days when we were all forced to look away? To truly appreciate the depth of this mystery, we need to talk about time. Because when I say we were unprepared for what happened on October 29th, I don't mean we were caught off guard in the traditional sense. This wasn't a cosmic hit and run like our first interstellar visitor, 1I Oumuamua, back in 2017. The discovery of Oumuamua sent shockwaves through the astronomical community precisely because we had absolutely no warning. We only spotted it on October 19, 2017, well after it had already slingshotted past the sun and was racing away from us on a hyperbolic escape trajectory. By the time we even realized it wasn't just another asteroid from our own solar system, but a visitor from the stars, it was already outbound, already fading, already slipping beyond the effective reach of our most detailed spectroscopic instruments. We got one fleeting chance to study it, and we missed most of the critical moments. It was like seeing a phenomenal creature for a split second as it vanished into the fog. We were left with fragmented data, intriguing anomalies, and a host of unanswered questions. But 3I Atlas was fundamentally different. This time we had the luxury of time. We had 5 full months, nearly half a year, from the moment the Atlas survey telescopes in Chile first detected the object on July 1, 2025. When it first appeared, it was a faint magnitude 18 object, dim enough that it required incredibly sensitive instruments to even spot, but more than bright enough for our modern equipment to track reliably. The astronomical community immediately knew something unusual was approaching. The initial orbital calculations were posted on the Minor Planet Center's Near-Earth Object Confirmation page, which is essentially a digital clearinghouse where preliminary observations from around the world are gathered and refined as more and more data accumulates. Within a matter of weeks, as observatories across the globe turned their attention to this new arrival, the trajectory was refined with increasing precision. By the middle of July, the verdict was in, and it was unequivocal. This object was not bound to our solar system. Its orbital eccentricity, a number that describes how stretched out an orbit is, was well above 1.0. In the language of gravitational mechanics, any eccentricity greater than 1 means an object is on an escape trajectory. It didn't originate here, and after its brief, fiery visit with our Sun, it was destined to return to the blackness of interstellar space. We were watching humanity's third confirmed interstellar object. Let me give you some context for why that title, and this particular object, matters so much. Oumuamua, our first visitor in 2017, entered our solar system with what's called a hyperbolic excess velocity of about 26 kilometers per second. Think of this as the coasting speed it carried with it from interstellar space, beyond any acceleration it got from our Sun's gravity. It was fast. It was tumbling in a way that suggested a very strange, elongated shape, and it showed no signs of outgassing like a normal comet. Then, in 2019, we discovered our second visitor, 2I Borisov. Borisov was different. It arrived with a hyperbolic excess velocity of roughly 32 kilometers per second, faster than Oumuamua, but still within the range of what our theoretical models predicted for objects being gravitationally ejected from other star systems. More importantly, Borisov behaved exactly like a comet. It outgassed, it developed a visible coma and tail, and its chemical signatures were broadly consistent with the comets born in our own solar system. It was weird simply because of where it came from, but it wasn't weird in how it behaved once it got here. 3I Atlas is a different beast entirely. Its hyperbolic excess velocity at perihelion reached approximately 58 kilometers per second. Let that number sink in for a moment. It's moving at nearly twice the interstellar cruising speed of Oumuamua and almost twice that of Borisov. This isn't just unusual, it is sitting at the most extreme edge of what we expect for objects just drifting randomly through the interstellar medium. An object moving this fast suggests one of a few possibilities. Either it was ejected from its home star system in an incredibly energetic and violent event, perhaps involving a close pass with a super-Jupiter planet, or a binary star system, or its trajectory was shaped by complex gravitational interactions we don't fully understand, or it's something else entirely. Speed matters. It dramatically affects how the object interacts with our sun's gravity. It shortens the time we have to observe it, and it determines the incredible stresses, both gravitational and thermal, that the nucleus experiences as it whips around the sun. A comet moving at 68 kilometers per second during its closest solar approach is being subjected to forces that would tear a loosely bound pile of ice and rock to shreds. Whatever 3I Atlas is, it has to be strong. It has to be structurally coherent enough to survive that passage intact. By September 2025, astronomers had refined its trajectory with extraordinary precision. They knew perihelion would occur on October 29th. They knew the closest approach distance would be about 1.36 astronomical units from the Sun, inside Earth's orbit, but not dramatically so. They knew the comet's path would carry it almost perfectly along the ecliptic plane, that flat, pancake-like disk where all the planets orbit. But it was coming in at a steep inclination of about 175 degrees. That inclination meant the comet was traveling retrograde, moving backward relative to the direction our planets orbit the Sun. A retrograde orbit isn't impossible, but it is highly uncommon for objects in our solar system, and it strongly suggests an origin far from the gravitational influences that shape our own comet reservoirs, like the Oort cloud. This was definitively an outsider, something formed in conditions utterly unlike the environment that birthed our own world. And crucially, they also knew by September that the solar conjunction would blind us during perihelion. The math was undeniable. The trajectory calculations made it glaringly obvious. On October 21st, the object would slip behind the Sun, and it would remain hidden through early November, long after the most critical moment had passed. Every single astronomer reviewing the data understood the problem. They had months to prepare, to find a workaround. But institutional inertia is a powerful force. Telescope time is allocated months, sometimes years, in advance through a highly competitive process. Space missions operate on rigid schedules with their own competing priorities. And perhaps most damningly, despite its unusual speed and bizarre trajectory, 3I Atlas was officially classified as just another active comet. Interesting, yes, but not extraordinary enough to justify disrupting the entire global calendar of established observation plans. And so, we watched it approach. We tracked its brightness as it grew from a faint magnitude 18 in July to a respectable magnitude 12 by October. We collected what spectroscopic data we could, when weather and telescope availability permitted. We built our models, refined our predictions, and published our papers. And then, as foretold by the unchangeable laws of physics, October arrived. The comet slipped behind the Sun, and all that preparation, all that anticipation, became utterly useless. The moment we had been tracking for 5 months happened in the one place in the entire solar system where we were guaranteed not to see it. Now we arrive at the heart of the matter, the core evidence that elevates 3I Atlas from a simple astronomical curiosity into a profound and enduring enigma. Because if this was merely a fast-moving comet from another star system, interesting to scientists but ultimately conventional, we wouldn't be having this conversation. The story would have ended with a shrug and a, "What a shame we missed perihelion." But the observations we do have the precious data collected in the months before. The solar conjunction rendered the comet invisible, contain a cascade of puzzling patterns anomalies that do not fit comfortably into the neat boxes of standard cometary science. And I am not talking about wild speculation or fringe theories found on obscure internet forums. I am talking about peer-reviewed findings, measurements taken by credible, world-renowned institutions using state-of-the-art instruments, and analyzed by career astronomers who have absolutely no professional interest in sensationalizing their work. These are the stubborn, inconvenient facts that show up in the data, whether we want them to be there or not. Let's start with one of the most glaring anomalies, its polarization. When light from the sun travels through space and reflects off a comet's nucleus and the dust in its coma, that light becomes polarized. You can think of light as a wave that vibrates in all directions. Polarization is when those vibrations get aligned in a specific orientation after bouncing off a surface. It's the same principle behind polarized sunglasses, which block glare by filtering out light waves that are vibrating horizontally. Astronomers measure this polarization to infer properties they can't see directly, like whether a comet's surface is icy, rocky, or covered in complex organic compounds. It is a standard diagnostic tool that has been applied to thousands of comets over decades of observation. We have an excellent, robust baseline of data for what normal comet polarization looks like. And 3I Atlas doesn't just deviate from that baseline, it shatters it. The polarimetry measurements taken before it disappeared behind the sun revealed an extreme negative polarization. This is a characteristic that is almost never seen in active comets. Instead, it's more commonly associated with a class of objects known as trans-Neptunian objects, or TNOs. Those distant primordial bodies orbiting in the frozen, dark, outer reaches of our own solar system, far beyond Neptune. Negative polarization suggests surface properties that are fundamentally different from the dusty, icy mantles that are typical of the comets we know. Among the more than 10,000 comets that have been observed with polarimetric techniques, 3I Atlas sits so far out on the distribution curve that it is a complete and utter outlier. That's not just unusual, it's unprecedented. Mainstream astronomers are trying to explain this away by suggesting it could be caused by very specific exotic mineral compositions in its nucleus or unusual dust properties in its coma. But even they admit it's deeply strange. It's a data point that requires a special explanation rather than fitting comfortably into our existing models. When your object is behaving like a pristine, untouched Kuiper belt object from the dawn of the solar system, despite simultaneously exhibiting clear cometary activity like outgassing and coma formation, you have a puzzle that does not resolve easily. Then there is the chemistry. NASA's James Webb Space Telescope, our most powerful infrared observatory, turned its golden eye towards 3I Atlas during its approach. The spectroscopic data it captured revealed the comet's chemical composition with extraordinary detail. What it found was both familiar and deeply unsettling. The comet contains many of the compounds we expect to see in solar system comets: water ice, water vapor, carbon monoxide, carbon dioxide, and even carbonyl sulfide. But the ratios, the fundamental recipe of this object, are all wrong. 3I Atlas is unusually, almost unnaturally rich in carbon dioxide, containing proportions that exceed the average for comets in our solar system by a significant margin. It is also actively emitting cyanide gas and, most bizarrely, atomic nickel vapor, both of which were detected through their characteristic spectral signatures. Now, cyanide isn't necessarily rare in comets. It's a known byproduct of organic chemistry in icy bodies. but vaporized nickel is far less common, suggesting either an unusual amount of metal content in its nucleus or heating patterns that are somehow vaporizing metals far more readily than our models would predict. This unique chemical signature is a message. It tells us something profound about where 3I Atlas was born. The abundance of carbon dioxide suggests it formed in a much colder, more carbon-rich environment than the region of the protoplanetary disk where our own solar system's comets originated. Different star systems have different elemental abundances, depending on the generations of supernovae that seeded the interstellar clouds from which they formed. If 3I Atlas comes from a system that was heavily enriched in carbon, its composition would make a certain kind of sense. But it also definitively marks this object as chemically distinct, a visitor carrying the indelible fingerprint of an alien stellar chemistry. When you analyze its spectrum, you are not just seeing a comet. You are seeing the ghost of a different star's planetary formation history. Now, we must step carefully into more controversial territory. There are claims circulating in independent astronomy communities, and I must stress, these are as yet unverified by mainstream observatories, but they are persistent enough to warrant a mention. Some observers report detecting pulsed signals in the 1.42 GHz frequency range emanating from the object AS vicinity. And these pulses are not random. They are allegedly arranged in what appears to be a Fibonacci sequence: 8, 13, 8, 5, 13, 8. If this is true, it would be the single most extraordinary discovery in human history. The 1.42 GHz frequency is not just any random spot on the radio dial. It corresponds to the spectral line of neutral hydrogen, the most abundant and fundamental element in the entire universe. It's a universal constant. SETI, the search for extraterrestrial intelligence. Researchers have monitored this cosmic water cooler frequency for decades, operating on the logical assumption that any advanced civilization trying to communicate across interstellar distances would recognize its universal significance. A signal at this precise frequency, organized in a clear mathematical pattern like the Fibonacci sequence, would be nearly impossible to explain as a product of natural outgassing or random plasma emissions from a comet. But again, I must emphasize, these claims remain unverified. No major observatory has published a confirmation of this pattern. No peer-reviewed paper has validated the methodology used to detect these pulses. We are in speculative territory here, relying on reports from amateur astronomers and independent researchers whose work has not yet survived the rigorous scrutiny of the scientific establishment. Maybe they are seeing something real that our mainstream instruments, for whatever reason, missed. Or maybe they are seeing noise and, through confirmation bias, are interpreting a pattern where none actually exists. Right now, we simply don't know. What we do know with absolute certainty is its orbital trajectory. 3I Atlas arrived on a hyperbolic path with an eccentricity of 6.137, higher than any previously confirmed interstellar object. This extremely high eccentricity means its path through our solar system was less of a gentle curve and more of a straight line with a sharp, violent deflection at perihelion. Its path also carried it nearly parallel to the ecliptic plane, that flat disk where the planets orbit, despite coming in at that steep retrograde inclination of 175 degrees. This combination, retrograde motion, ecliptic alignment, and extreme eccentricity, is mathematically possible, but it is statistically incredibly rare. Random objects drifting through the void can approach from any direction, at any inclination. The fact that 3I Atlas came in almost perfectly parallel to the plane of our planetary orbits strikes some astronomers as a profound coincidence. Others argue that, given the vast number of potential interstellar objects passing through our galaxy, such alignments are bound to happen eventually. Your interpretation depends entirely on whether you think one highly unusual case is enough to suggest a pattern, or whether you need multiple examples before you dare to draw any conclusions. Finally, there's the deep uncertainty about its size. Estimates for the diameter of its nucleus range from as small as 0.32 kilometers to as large as 5.6 kilometers. That is a massive range of uncertainty for an object we observed for 5 months. The problem is that an object's brightness doesn't directly tell you its size unless you also know its reflectivity, a property called albedo. A small, highly reflective object, like a ball bearing, can appear just as bright as a large, dark object, like a lump of coal. Without direct imaging that is clear enough to resolve the nucleus's actual dimensions, we are forced to infer its size from its brightness, and that inference is based on assumptions about its surface properties. And what if those assumptions, based on our knowledge of our own solar system's comets, are completely wrong? If 3I Atlas has an unusually high albedo, perhaps due to a surface of pristine ice or even reflective mineral or metallic coatings, it could be much, much smaller than its brightness suggests, and a smaller size creates an entirely different problem. How can a sub-kilometer nucleus produce the significant levels of outgassing and the bright coma that we observed? A smaller comet with such high activity implies it's either made of unusually volatile ices that vaporize more easily, or its composition is something we simply don't understand yet. Put all of these anomalies together: the unprecedented polarization, the alien chemistry, the unverified but persistent emission claims, the statistically rare trajectory, and the profound size uncertainty, and you get an object that steadfastly resists any comfortable categorization. Mainstream astronomers handle this by saying that comets are a diverse family of objects, and that outliers are to be expected. They point to other oddball comets in our own history, like Comet Hale-Bopp's surprising brightness or Comet Shoemaker-Levy 9's fragmentation, as proof that the category of Viad comet contains far more variation than we sometimes acknowledge. And they are not wrong. An anomaly does not automatically equate to a non-natural origin. But when you have this many powerful anomalies all clustered together in one object, an object that is moving faster than almost anything we've ever seen arriving from interstellar space on a trajectory that just so happened to perfectly hide it from us during its most revealing moment. Well, that combination makes some people, very serious people, start to ask whether we are truly looking at all the possibilities. This is the point where the path of inquiry splits, where intellectual honesty demands that we examine the two competing frameworks for understanding what 3I Atlas actually is. This is where you, the viewer, need to see the evidence that each interpretation handles well, and where each one struggles, so that you can make your own informed judgment about which explanation fits the available data more comfortably. I'm not here to tell you what to believe. I am here to show you exactly why this intense and fascinating debate exists in the first place. On one side, we have the mainstream interpretation. It is straightforward, logical, and admirably parsimonious. In this view, 3I Atlas is an active comet from another star system. It was born in the protoplanetary disk of a distant star, and at some point in its history, it was ejected into interstellar space through a powerful gravitational interaction, perhaps a close encounter with a giant planet like Jupiter, or perturbations from a passing star that destabilized its orbit. It then drifted through the cold, dark void of interstellar space for hundreds of thousands, perhaps millions, of years, until its trajectory, by pure chance, happened to intersect with our solar system. As it fell inward toward our sun, the increasing solar heating began to vaporize the ancient ices on its surface, producing the coma and the outgassing that we associate with cometary activity. Its unusual speed, while high, is not physically impossible. Objects ejected from other star systems, especially from the chaotic environments of binary stars or dense star clusters, can carry significant velocities. The unique chemical composition, with its high carbon dioxide content and other volatile ratios, simply reflects the fact that it was formed in a different stellar environment, one that had different elemental abundances than our own. The extreme negative polarization, while exceptionally rare, can be plausibly explained by specific mineral compositions or unique dust properties that we just haven't fully characterized yet. In this view, every single anomaly, when examined individually, has a plausible, if sometimes strained, natural explanation that does not require invoking any extraordinary claims. Comets are diverse, and interstellar comets are likely to be even more so because they represent a sample of formation conditions from across the galaxy. Therefore, 3I Atlas is interesting. It is scientifically valuable, and it is absolutely worthy of continued study. But ultimately, it is a comet. This interpretation has significant and undeniable strengths. It aligns perfectly with the principle of Occam's razor, the philosophical idea that, when faced with competing explanations, the one requiring the fewest new assumptions should be preferred until overwhelming evidence forces us toward a more complex model. It comfortably handles the bulk of the observational data, the brightness variations, the spectroscopic signatures of known molecules, the outgassing rates. All of these broadly match the cometary behavior we have documented in thousands of objects from our own solar system. It doesn't require us to postulate any unknown physics or to invoke the specter of non-natural technological origins. And, perhaps most importantly, this is the consensus view among the vast majority of institutional astronomers who have reviewed the data. When NASA or the European Space Agency describes 3I Atlas in their official communications and press releases, they call it an interstellar comet. Full stop. There are no caveats, no official acknowledgments of profound strangeness, and no speculation that anything unusual requires a deeper investigation beyond the boundaries of standard cometary science. But then, there is the other interpretation. This viewpoint is championed most prominently and most articulately by Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University, and the former chair of Harvard's prestigious astronomy department. Dr. Loeb is not a fringe figure or an internet crackpot. He is a deeply respected scientist who has published hundreds of peer-reviewed papers, has advised dozens of graduate students, and has built a formidable career studying some of the most profound subjects in the cosmos, including black holes, cosmology, and the early universe. In recent years, he has also become the most visible and courageous advocate for taking seriously the possibility that some astronomical anomalies might, in fact, indicate the presence of technological artifacts rather than purely natural phenomena. And 3I Atlas, in Dr. Loeb's detailed analysis, exhibits not one or two, but 9 distinct and powerful anomalies that, when taken together as a collective whole, resist a comfortable classification as just another typical comet. Dr. Loeb's framework does not claim certainty. He is a scientist, and he explicitly acknowledges that extraordinary claims require extraordinary evidence, and that the evidence for 3I Atlas remains frustratingly incomplete. But he also argues, quite powerfully, that dismissing anomalies simply because they make us uncomfortable, or because they challenge our preconceived notions, is the very definition of bad science. So let's look at his 9 points, his catalog of strangeness. First, the extreme negative polarization, unprecedented among active comets. Second, the unusual chemical composition, particularly the high carbon dioxide abundance. Third, the statistically improbable trajectory alignment with the ecliptic plane, despite its retrograde motion. Fourth, the extraordinarily high speed of 68 kilometers per second at perihelion. Fifth, the puzzling size-to-brightness ratio, which suggests either an unusual albedo or non-standard surface properties. Sixth, the almost impossibly convenient timing of the solar conjunction during perihelion, which prevented any Earth-based observation at the most critical moment. Seventh, the reported but still unverified emission patterns at the 1.42 GHz hydrogen line frequency. Eighth, Its close proximity to the planet Mars on October 3rd, just weeks before perihelion, offering a potential observation point from a different angle. And ninth, the comet's origin direction. This last point deserves special elaboration because it is by far the most speculative and also the most fascinating. On August 15, 1977, Ohio State University's Big Ear radio telescope detected a powerful narrowband radio signal that lasted for a full 72 seconds. The signal appeared in a frequency range consistent with an artificial transmission. It was so striking, so unlike any natural signal ever detected, that the astronomer on duty, Jerry Amon, famously wrote the word "wow" in the margins of the computer printout. Despite decades of repeated attempts to redetect it, the signal has never recurred. Its origin remains one of the greatest unsolved mysteries in modern science. Mainstream SETI researchers have generally attributed it to a fleeting terrestrial interference source or some rare, natural astrophysical phenomenon that we still don't fully understand. But Dr. Loeb's analysis suggests that 3I Atlas originated from a region of the sky only 9 degrees away from the source direction of the WOW signal. He calculates the probability of this alignment occurring purely by chance as approximately 0.6%. Low, but not impossibly low. As he notes, if you have 100 interstellar objects, you'd expect at least one to align this closely with any given point in the sky, just by random chance. But it's the kind of coincidence that should make you pause and take a very deep breath. Dr. Loeb's hypothesis isn't that 3I Atlas is definitively an alien spacecraft. He frames it far more carefully, as a scientist should. Could this object, he asks, exhibit signatures that are consistent with a technological artifact? Perhaps an autonomous probe on a survey mission, or even a derelict piece of ancient technology tumbling through space. Could some of its anomalies, especially the extreme polarization and the possible emission patterns, be indicators of engineered materials rather than natural ice and rock? He emphasizes that resolving this question requires better data, specifically the very observations we were denied during perihelion because of the solar conjunction. But he also argues that science only advances by investigating the outliers, not by explaining them away prematurely to preserve the status quo. The tension between these two interpretations boils down to a fundamental question of how you weigh anomalies. If you believe that comets are diverse enough that any single anomaly, no matter how strange, can eventually be accommodated within the bounds of natural variation, then 3I Atlas is just an unusual comet. But if you think that the clustering of so many independent anomalies in one single object deserves much closer scrutiny, especially when that object also happens to be perfectly hidden during its most revealing moment, then you start to ask a very different set of questions. You start to wonder whether our rigid categorical framework of natural versus artificial is too simplistic. You start to wonder if hybrid possibilities exist that we haven't even begun to consider. What if 3I Atlas is a natural comet that just happened to pass through a region of space containing technological debris, accumulating surface coatings or embedded fragments that alter its observational signatures? What if it's an ancient artifact, launched millennia ago by a civilization long since gone, now defunct, and tumbling through space, looking almost identical to a comet, except under the most detailed spectroscopic examination? These are the questions that can't be answered definitively with our current, incomplete data. And that is the frustrating, tantalizing reality. We have suggestive anomalies, but no smoking gun. We have competing frameworks that each handle different subsets of the data better than the other. And we have that gaping observational hole during perihelion that prevents us from obtaining the very measurements that might finally resolve the debate. Either explanation, a strange natural comet, or a technological artifact, remains possible. But the possibility itself, the very fact that we are even having this conversation with peer-reviewed research and serious academic debate, supporting both sides, tells you something incredibly important about where we are in our journey of understanding what truly moves through the vast dark spaces between the stars. And now we must confront the central mystery, the element that transforms the story of 3I Atlas from a mere astronomical curiosity into something that feels almost like a meticulously crafted thriller. The timing. The timing of the solar conjunction relative to the object's perihelion wasn't just a stroke of bad luck, and it certainly wasn't an oversight by astronomers who should have planned their observations better. It was the absolute inevitable consequence of the comet's trajectory. It was predetermined from the very moment 3I Atlas first entered our solar system, locked into place by the unforgiving laws of orbital mechanics that could not be altered without invoking some kind of unseen, unobserved force. And that very inevitability, that clockwork precision, raises a question that almost nobody wants to ask out loud, because of how deeply it challenges our view of the cosmos. The question is this: if you were designing a trajectory for a probe to pass through our solar system while remaining completely unobservable during its most revealing and vulnerable moment, could you possibly do any better than the actual path that 3I Atlas took? Let me walk you through the geometry again, so you understand exactly why this question matters so much. On October 21, 2025, a full 8 days before it reached perihelion, 3I Atlas crossed behind the Sun from Earth's perspective. The technical term, solar conjunction, is the moment when an object's angular separation from the Sun, as viewed from our planet, becomes so small that observation becomes impossible without pointing our most sensitive instruments dangerously close to the solar disk. For 3I Atlas, this conjunction wasn't a brief, fleeting event. Starting in early October, the comet's solar elongation, its apparent distance from the Sun in our sky, dropped below 30 degrees, entering a zone where even our most advanced space telescopes would struggle to collect any useful data against the overwhelming glare. By October 21st, that elongation reached its absolute minimum. The comet was positioned almost directly behind the Sun, and it remained locked in that observational dead zone all the way through early November, more than a week after perihelion had already passed. Think about what perihelion truly represents for a comet. It is the moment of trial by fire. It's the instant of maximum solar heating, when the nucleus experiences temperatures capable of vaporizing not just the surface ices, but also the more deeply buried subsurface volatiles, driving outgassing rates to their absolute peak. It's the moment when thermal stress can literally fracture the nucleus, causing it to break apart and reveal its internal structure. It is the moment when any unusual properties, an abnormal albedo, an unexpected chemical composition, or surface features inconsistent with natural formation, would become most glaringly detectable because the object is at its brightest and its most active. For any interstellar visitor, perihelion is the moment of truth. It's the instant when we learn what it's actually made of, how it responds to the intense radiation of our own Sun, and whether it behaves like the objects that were formed in our own stellar neighborhood, or reveals characteristics that are fundamentally alien to the bodies we know. Missing the observation of perihelion is like preparing for months to conduct a crucial, live interview with a reclusive and important figure, only to have them cancel at the very last second. You still have all the background information you gathered beforehand, but you have lost the one and only chance you had to ask the questions that truly matter. And again, astronomers knew this gap was coming. The trajectory calculations performed back in July and refined through August and September made it blindingly obvious that perihelion and solar conjunction would nearly coincide. They had months upon months to coordinate alternative observation strategies. So why didn't they? Part of the answer, as we discussed, is simple institutional inertia. Telescope time is a fiercely competitive and limited resource, allocated through proposal processes that happen months or even years in advance. Redirecting a major, flagship space telescope like the James Webb or Hubble towards a new, unscheduled target of opportunity requires a level of justification so strong that it can displace already approved, long-planned science programs. And 3I Atlas, despite all of its strangeness, was not officially classified as being extraordinary enough to warrant that level of disruption. It was fast, yes. Its chemistry was interesting, certainly. But NASA's official assessment categorized it simply as an active comet, scientifically valuable, but not unprecedented. Then there is the Mars angle, which remains frustratingly and suspiciously under-discussed in most mainstream coverage. On October 3, 2025, the planet Mars was positioned at just 0.19 astronomical units from 3I Atlas's trajectory. That is incredibly close, significantly closer than Earth would get at any point during the comet's passage. The European Space Agency's Mars Express orbiter, a spacecraft that has been studying Mars from orbit since 2003, carries instruments that are perfectly capable of observing comets from a completely different vantage point than Earth. If coordinated observations had been prioritized, Mars Express could have provided invaluable spectroscopic and imaging data during the exact period when all of our Earth-based telescopes were completely blinded by the solar conjunction. But as of right now, in early December 2025, there has been no public data released from Mars Express that confirms whether the spacecraft even targeted 3I Atlas, and if it did, what it observed. That silence is interesting. It might mean nothing at all. Data processing from deep space missions takes time, and government space agencies operate on schedules that do not prioritize rapid public disclosure. Or, it might mean something worth paying very close attention to. What we did get from Earth orbit were those fragmentary, tantalizing observations from satellites that were never designed for this kind of work. NASA's GOES-19 weather satellite captured those images of a magnitude 12 object. SOHO recorded its passage through its coronagraph. These observations confirmed the object's existence and its trajectory. They provided a rough measurement of its brightness, but they lacked the spectral resolution to reveal its chemical composition. In detail, the temporal resolution to track rapid changes in outgassing, and the raw sensitivity to detect the subtle features that might differentiate this object from a conventional comet. It was like trying to understand a symphony by listening to it through a wall with a tin can and a string. You know something is happening, but you miss all the nuance, all the detail, all the meaning. The timing of this feels almost perfectly designed to frustrate any deep investigation. Now, I am not suggesting that the comet deliberately chose its trajectory, but it is designed in the sense that if you were to map out all possible hyperbolic trajectories through our solar system, and then ask a computer which of those trajectories would most effectively hide the perihelion event from Earth-based observation, the path of 3I Atlas would rank among the most effective. It approached nearly along the ecliptic plane, which ensured that its conjunction would occur at a very small solar elongation, rather than passing harmlessly above or below the Sun's position in our sky. It timed its perihelion to occur just a few days after the conjunction reached its minimum, ensuring that its closest approach happened deep within the observational dead zone. And it moved so fast that the window for detailed pre-conjunction observation was incredibly narrow. By the time astronomers had fully characterized its unusual properties in September, October was already arriving, and the conjunction was imminent. Coincidence or consequence? That depends entirely on how you choose to interpret the cold, hard facts of orbital mechanics. In a deterministic universe, everything that happened was inevitable from the moment 3I Atlas entered our system. Its trajectory was set. The conjunction timing wasn't a choice, it was an outcome. But outcomes can still be remarkably convenient for some purposes, and remarkably inconvenient for others. If the goal was to pass through our solar system while minimizing detailed observation during the most revealing moment, this trajectory accomplished that goal with breathtaking efficiency. Whether that was by pure accident or by something more akin to intention, is the one question we currently cannot answer. So here we are, in the aftermath, staring into a void of missing data. Let me tell you exactly what remains unknown about October 29, 2025, and why those unknowns matter more than anything we have already established. Because here is the harsh reality of our situation. Everything I have described to you so far, the catalog of anomalies, the two competing interpretations, the speculative but tantalizing connections, all of it exists in a state of unresolved, almost unbearable tension. We have a collection of observations that strongly suggest something incredibly unusual passed through our cosmic neighborhood, but we lack the one definitive smoking gun measurement that would force a scientific consensus one way or the other. And that lack of data isn't temporary. It isn't something we can fix by building a bigger telescope or allocating more funding. It is permanent. The moment of perihelion has passed. It is gone forever. And you cannot rewind time to go back and capture the light you missed. We are left with a legacy of questions that may, in fact, never be fully answered. And the sheer weight of those questions defines how we should think about what comes next. First, we don't know the exact state of the nucleus during perihelion. Did the object undergo the intense thermal stress sufficient to cause fragmentation? Did it split into multiple, smaller pieces that will now gradually disperse as they travel away from the Sun? Fragmentation would eventually show up in our post-perihelion observations as multiple bright condensations within the coma, or perhaps as an abnormally rapid decline in the object's total brightness as those fragments spread out and fade. But distinguishing that kind of event from the normal fading of a comet as it recedes from its heat source requires the very baseline measurements during perihelion that we do not have. We can compare the pre-conjunction brightness to the post-conjunction brightness and look for deviations from our predicted models. But those comparisons will always be indirect. They will tell us the outcome, not the process. If the comet broke apart on October 29th, we will have to infer it from the after effects, not from the profound experience of having watched it happen. Second, we don't know if its chemical composition fundamentally shifted during the moment of maximum heating. Cometary nuclei are not uniform blobs of ice. They are layered structures, like cosmic onions, with surface layers of ice and dust covering deeper reservoirs of more volatile compounds, things like carbon monoxide, methane, nitrogen, exotic ices, that only begin to sublimate at much higher temperatures. As the Sun heats the nucleus during its close approach, these subsurface layers should begin to vaporize, releasing new gases into the coma that may not have been present earlier in the trajectory. Real-time spectroscopy during perihelion would have revealed this chemical evolution as it happened, allowing us to map which volatiles emerged at which specific temperatures. Our post-perihelion spectroscopy, which we are conducting now in December as the comet fades, will show us the composition after the heating event. But we will never have seen the transition. If any unusual or exotic chemical species appeared briefly during perihelion, and then disappeared just as quickly as the comet cooled, we would have missed them entirely. Third, we do not know for certain whether its orbit underwent any measurable deflection beyond what our gravitational predictions can account for. These non-gravitational forces, the tiny jets of outgassing acting like miniature rocket engines, can gently nudge a comet's trajectory in ways that deviate slightly from a purely gravitational path. Detecting this kind of acceleration, however, requires incredibly precise tracking before, during, and after the forces are acting. We have excellent pre-conjunction trajectory data, and we will have excellent post-conjunction data. But that gap during perihelion means we are missing the very period when these non-gravitational forces would have been at their absolute strongest. We can fit a trajectory model to the before and on after Trident positions, and try to infer whether some kind of anomalous deflection occurred in between, but the uncertainty in that calculation will be significantly larger than if we had been able to track it continuously. Any small but significant anomalies could easily be hidden within that margin of error. And finally, we don't know whether any unexpected emissions or signals occurred during that solar conjunction period. If those Fibonacci pulse patterns reported by independent observers are real, perihelion would have been the most likely time for them to intensify, assuming they are related to some internal process that is activated by solar heating. But any radio observation during that period was hopelessly compromised by the sun's own immense radio noise, which dominates the entire electromagnetic environment in the inner solar system. Trying to detect a weak, patterned signal from a small object positioned directly behind the sun is like trying to hear a person whispering a secret from across a stadium during the roar of a rock concert. It is next to impossible. Even if 3i Atlas was shouting a message to us, we almost certainly would have missed it simply because the sun's own radio output would have drowned everything else out. But here is what we will know, or at least what we should know, within the next few months. By now, December 2025, the comet has exited the solar conjunction zone and is once again observable from Earth, though it is now significantly fainter than it was during its approach. The post-perihelion spectroscopy will reveal its current chemical composition, allowing for a direct comparison with the measurements we took back in September. If the volatile ratios have changed, that will tell us something profound about how its nucleus responded to the intense heat. If the polarization measurements have shifted, either returning to values more typical of normal comets or remaining anomalously negative, that will inform the debate about its surface composition. And if its brightness declines faster or slower than our models predict, that will help us constrain our estimates of its true size and its outgassing efficiency. And of course, the Mars-based observations, if they were conducted, might finally emerge in the coming weeks or months. That data could provide a crucial, independent perspective. Then, there is March 2026. On March 16th, 3i Atlas will pass within 0.36 astronomical units of the giant planet Jupiter. Jupiter's powerful gravitational field will deflect the comet's trajectory one last time, providing a final, crucial opportunity for observation before the object exits the inner solar system and becomes too dim for any detailed study. This flyby matters because any permanent changes that were caused by the perihelion passage, fragmentation, altered outgassing patterns, surface modifications, will be clearly visible during this close Jupiter approach. If we are going to definitively characterize 3i Atlas as either a normal, albeit strange, comet, or as something more unusual, March 2026 is our absolute deadline. After that, it races outward on its hyperbolic path, moving too fast for our sun's gravity to ever capture it. Within a few short years, it will be gone, returning to the blackness of interstellar space, becoming one more dark, silent, invisible object drifting through the galaxy. If we haven't answered the key questions by then, we likely never will. The window is closing. The larger significance of this story of 3i Atlas extends far beyond this one object. Every interstellar visitor we detect is a lesson. It teaches us about the conditions in other star systems, about the planetary formation processes that operate in environments unlike our own, and about the sheer diversity of objects that move through our galaxy. If 3i Atlas is just a comet, it is an extreme and valuable example, pushing the known boundaries of what we thought comets could be. But if it is something else, if even a fraction of the speculative hypotheses hold any validity, then it could represent the first technologically detectable artifact from beyond our own solar system. Either conclusion fundamentally reshapes our understanding of the universe and our place in it. But for now, we are in limbo. We have enough anomalies to justify a deep and continued investigation, but not enough definitive evidence to demand any extraordinary conclusions. We have two competing frameworks that each explain different subsets of the data, but no single framework that can handle everything comfortably. And we have that gaping observation hole, that missing chapter, a gap imposed by the simple, cruel geometry of orbital mechanics that prevents us from obtaining the very data that might resolve this profound uncertainty. So where does that leave us? It leaves us here, watching. It leaves us monitoring the post-perihelion observations as they are released, comparing them to our baselines, looking for the subtle changes that might reveal what happened behind the sun. It leaves us waiting, with bated breath, for March 2026, when Jupiter's gravity gives us one final chance to study this object up close. And it leaves us asking the hard questions that institutional science sometimes avoids, not because those questions are unscientific, but because they challenge our most comfortable assumptions about what we expect to find when we look up at the sky. The story of 3I Atlas is a powerful lesson, one that we can all apply to our own lives. It's a lesson about the danger of certainty and the profound importance of humility and curiosity. How often in our own lives do we think we have all the data? How often do we draw firm conclusions based on an incomplete picture? This object reminds us that there are always blind spots, moments when we cannot see the whole truth. It teaches us to question the easy narrative, to pay attention to the anomalies, the things that don't quite fit, whether it's in our relationships, our careers, or our understanding of the world. The most important truths are often hidden in the data we missed, or in the questions we were too afraid to ask. The universe kept a secret from us on October 29th. The lesson is not to be frustrated by the secret, but to be inspired by the mystery. So I ask you, what do you think we're looking at? An unusual but natural comet shaped by alien stellar chemistry, or something more? What single piece of evidence, if it were discovered, would convince you one way or the other? Are you ready to wait until March 2026 to find out what happens when 3I Atlas passes Jupiter and we get our last clear look? This mystery isn't over. In many ways, it's just beginning. And you are here, right now, at the moment when we still have a chance to solve it. Let's see what comes next. Thank you for joining me on this journey into the unknown. I wish you and your loved ones clear skies and good health. Don't forget to subscribe to the channel so you won't miss our follow-up when new data emerges.